In this video, we will talk about the petroleum reservoir geology. Petroleum reservoir geology is the study of underground rock formations that store and transmit oil and natural gas. These reservoirs are crucial for extracting energy resources. Reservoir rocks like sandstones, limestones, and dolomites have tiny spaces called pores that store fluids. The ability of these rocks to let fluid pass through is called permeability. Reservoirs are trapped underground in different ways. Structural traps form when rock layers bend or break. Stratigraphic traps occur because of change in rock types. Sometimes a combination of both traps the oil and gas. Cap rocks, like shale or salt, are layers that prevent hydrocarbons from escaping. This keeps the oil and gas stored underground. Inside the reservoirs, you'll find crude oil, natural gas, and water. Geologists explored these reservoirs using seismic surveys and drilling. Once found, the hydrocarbons are extracted through wells. Understanding petroleum reservoir geology is essential for efficiently extracting energy while minimizing environmental impact. Let's define what a reservoir is in the context of oil and gas. A reservoir is a subsurface rock formation that has three key characteristics. Porosity: it contains empty spaces called pores that can store fluids like oil, gas, or water. Permeability: these pores are connected, allowing fluid to flow through the rocks. Trap and seal: it's covered by an impermeable layer that prevents hydrocarbons from escaping. In simple terms, a reservoir is a natural storage space for hydrocarbons waiting to be extracted. In this slide, we'll discuss reservoir rocks and sealing rocks, both of which play a crucial role in oil and gas accumulation. Reservoir rocks store hydrocarbons and must have high porosity to hold fluids and good permeability to allow flow. They are classified into two types: clastic reservoirs like sand and gravel, which have intergranular porosity, meaning fluids are stored between the grains. Carbonatic reservoirs such as limestone and dolomite. Limestone has multiple porosity types, including fractures and vuggy porosity, while dolomite mainly has intercrystalline porosity. So, the petrophysical characteristics of reservoir rocks. Porosity ranges from 5% to 35%, and permeability varies between 10 to 10,000 millidarcies. Unit is millidarcy, allowing hydrocarbons to move easily. Sealing rocks trap hydrocarbons and prevent their movement. Common examples include salt, anhydrite, shale, clay. Unlike reservoir rocks, they have low porosity, that is 0 to 5%, and extremely low permeability, less than 0.1 millidarcy, making them effective barriers. In summary, reservoir rocks store and allow hydrocarbons to flow, while sealing rocks trap them underground, preventing escape. Both are essential for forming oil and gas reservoirs. Hydrocarbons are trapped in subsurface rock formations due to different geological structures. There are four main types of trap that prevent oil and gas from escaping. First, we have the anticlinal trap. It forms when rock layers fold upward, creating a dome-like structure. Oil and gas migrate to the highest point and get sealed beneath impermeable shale. This is one of the most common and productive traps. Next is the fault trap. Caused by rock displacement along a fault line, the movement blocks hydrocarbon migration, trapping oil and gas against the impermeable rock. Then there is the stratigraphic trap, which forms due to change in rock layers rather than structural deformation. This can happen when reservoir rocks pinch out or are cut off by impermeable layers, creating a natural trap. Finally, the salt dome trap occurs when rising salt formation deforms surrounding rocks. The impermeable salt act as a barrier, trapping hydrocarbons in the adjacent reservoirs. In all these traps, impermeable layers like shale or salt acts as a seal, preventing hydrocarbons from escaping. Since oil and gas are lighter than water, they accumulate at the highest point within these traps, making them crucial for petroleum exploration. Stratigraphic traps form due to natural change in rock layers over time, creating barriers that trap oil and gas underground. Unlike structural traps, these don't rely on folding or faulting but rather on variation in sedimentation. One type is the sandstone lens, where porous sandstone is enclosed by impermeable rock, holding hydrocarbons inside like a natural container. Then we have the sandstone pinch out, where a sandstone layer thins out and disappears, causing oil and gas to accumulate at the point where it meets impermeable rock. Next is the unconformity trap, which forms when older rocks are eroded before new ones are deposited. If a porous rock is sealed by an impermeable layer at this boundary, it becomes an effective reservoir. Lastly, the reef trap develops in the ancient reef system. Corals and marine life create structures with high porosity, which later get sealed by surrounding sediments, trapping hydrocarbons inside. Stratigraphic traps are crucial in oil exploration because they often hold large hidden reservoirs. Unlike obvious structural traps, finding them requires detailed geological studies, but they play a major role in global oil production. This diagram shows how surface features like rivers, lakes, and floodplains connect to subsurface sedimentary deposits, which can act as hydrocarbon reservoirs. At the surface, a winding river moves across the landscape, depositing sediments. Surrounding floodplains consist of fine-grained silts and clays, while lakes accumulate thinly bedded shales that can later act as seals. Below the surface, riverbank and channel faces hold cross-bedded, coarse-grained sands and conglomerates, highly porous and excellent for trapping hydrocarbons. Floodplain deposits made of clays and silt reduce permeability, creating natural barriers. Meanwhile, lake deposits form sealing layers that prevent hydrocarbons from escaping. Understanding these structures is crucial in petroleum exploration. It helps geologists determine where to drill, how much oil or gas may be present, and how fluids will move within the reservoir, directly impacting production efficiency. This type of reservoir characterization is essential for identifying high-quality reservoir rocks and effective sealing for formation in subsurface geological settings. This image represents sedimentary environments, places where sediments are deposited and eventually form rocks. We start with continental environments, alluvial fan, cone-shaped deposit from fast-flowing streams near mountains, braided rivers, intervening channels carrying coarse sediments, wetlands and lakes, low-energy zones where fine sediments settle, anastomosing rivers, multiple stable channels separated by vegetated islands. Next, we move to transitional environments where land meets sea. Tidal flats, coastal muddy zones shaped by tides, leaves, natural embankments formed along riverbanks, crevice splays, sediment bursts from river flooding, lagoons, shallow water shielded by barrier islands, beaches, high energy sandy shores shaped by waves. Finally, we explore marine environments. Shore face, the near shore zone impacted by waves, offshore transition zones where fine sediments settle. Deep offshore, the deep sea accumulating fine grained deposits. Why does this matter? These environments determine how rock form, influencing oil and gas reservoirs, land use, and geological studies. Understanding them is crucial for petroleum geologists, sedimentologists, and environmental scientists. This image illustrates hydrocarbon exploration in the Gulf of Mexico, highlighting how salt structures influence oil and gas accumulation. Salt sheets shown in the white are massive underground formations. These act as natural traps, allowing hydrocarbons to accumulate beneath them. The red dots indicate discovered oil and gas fields. Black dots represents wells that were explored but found unproductive. Key offshore fields like teak, mahogany, Gemini, and Enchilada are labeled along with coastal cities like Houston, New Orleans, and Lake Charles. Why does this matter? Salt structures create seals that trap hydrocarbons, making the Gulf of Mexico a crucial oil producing region. Understanding salt tectonics helps companies pinpoint drilling locations for potential petroleum reservoirs. A hydrocarbon prospect. What does it mean? It's an area where experts believe oil or gas might be found in large enough quantities to be worth drilling. Geologists analyze seismic data, looking for anomalies, unusual patterns that hint at hidden oil or gas reserves. To decide where to drill, they check for key signs: a good reservoir rock to store oil or gas, a trap to hold hydrocarbons in place, a proper seal to prevent leakage, evidence of oil or gas migration. A prospect is one specific location for drilling, while a play is a large region with multiple prospects. Why does this matter? Drilling is expensive. Identifying a strong prospect helps companies reduce risk and increase the chance of a successful oil or gas discovery. Next slide. How do geologists decide where to drill for oil or gas? First, they use a structure map. This top-down view shows underground rock layers. Depth markers like 7,500 and 8,000 feet indicate elevation. The highest point in the anticline marked as location is the planned drilling site. Next, the cross-section provides a side view. It highlights key layers: source rock, where oil and gas form; reservoir rock, where hydrocarbons are stored; cap rock, which seals everything in place. The trapping fault and anticline creates an ideal setup for oil and gas accumulation in the sand X layer. This method helps companies pinpoint the best drilling spot, reducing the risk of dry wells and increasing the chances of a successful oil or gas discovery. Next slide. Understanding key terms in hydrocarbon estimation. First, OHIP, or original hydrocarbon in place. This is the estimated total volume of hydrocarbons in reservoir before any production begins. Next, reserves. This represents the amount of hydrocarbons that can actually be extracted using current technology under a defined development plan. Finally, the recovery factor. It is calculated as reserves divided by OHIP, showing how much of the total hydrocarbons can be recovered. This calculation helps determine the efficiency of hydrocarbon extraction and guides production strategies. Next slide. Calculating the volume for hydrocarbons in place. OHIP, or original hydrocarbon in place, estimates the total hydrocarbon volume in a reservoir before production begins. The formula for OHIP is shown here. OHIP equals gross bulk volume multiplied by net to gross ratio, porosity, and the fraction of hydrocarbons in the pore space, divided by the formation volume factor. Each term plays a key role. GBV is the total rock volume, that is gross bulk volume. N/G represents the portion containing hydrocarbons, that is net to gross ratio. Phi shows the porosity, indicating storage capacity. SW accounts for water presence, that is your water saturation. And FVF, that is formation volume factor. This calculation is essential for estimating the total recoverable hydrocarbons in the field. So breaking down the key OHIP parameters that estimate hydrocarbons in a reservoir. Gross bulk volume, represented by the black shape, it shows the total size of the reservoir including both productive and non-productive rock. Net to gross ratio, seen in rock samples, this tells us how much of the total rock volume actually holds hydrocarbons. Porosity, the scattered black shape represents pore spaces in the rock where hydrocarbons can be stored. Higher porosity means more storage capacity. Water saturation, represented by SW. The blue areas indicated water-filled pores, while red represents hydrocarbon-filled pores. Lower SW means more hydrocarbons, making the reservoir better for production. Together, these factors determine how much oil or gas is available before production starts. Now breaking down the step-by-step process of calculating OHIP. Gross bulk volume, the total volume of the reservoir rock including both productive and non-productive areas. Net bulk volume, by multiplying the gross bulk volume with net to gross ratio, we remove non-productive rock, leaving only the portion that can hold hydrocarbons. Net pore volume, not all rock is solid. Some have tiny pores that store fluids. So multiplying the net bulk volume by the porosity gives us the total pore volume. Original hydrocarbon in place. Since some pores contain water, we remove that portion by multiplying the net pore volume by 1 minus SW, where SW is the water saturation. This process filters out non-productive rock and water, helping estimate the actual hydrocarbons in reservoir before production starts. Understanding porosity and its role in hydrocarbon storage. The equation at the top calculates OHIP, that is your original hydrocarbon in place, GBV, total rock volume, N over G, productive rock portion, porosity, pore space percentage, SW, water filled portion of pores, FVF, adjusts for volume changes from reservoir to the surface. Porosity highlighted in the equation is crucial. It determines how much fluid the rock can store. So what is porosity? The empty spaces between rock grains. More pores mean more fluid storage. The diagram shows solid grains and blue pores represent empty space. So how porosity calculated? It is calculated by the formula that is pore volume divided by pore volume plus grain volume. It represents the fraction of rock that is empty space. What affects porosity? Grain shape and compaction. Tightly packed grain reduce porosity. Grain packing and cementation. More cement means fewer pores. Grain sorting and clay content. Poor sorting fills gaps, lowering porosity. Porosity is key in oil and gas reservoirs, showing available spaces for hydrocarbons, but some of that space contain water, which can account for SW, water saturation. This image explains the net to gross ratio. which helps determine how much of rock formation is actually a reservoir rock, able to store and produce hydrocarbons, versus non-reservoir rock like shale, which doesn't store hydrocarbons well. Let's break it down. What is net to gross ratio? The left diagram shows a vertical rock column made up of alternating layers of sand, yellow portion, and the shale, that is the brown portion. The sand layers are usually reservoir rocks because they have high porosity and permeability. Shale layers are non-reservoir rocks because they act as a barrier. Net to gross ratio tells us how much of the total rock column is actually useful for hydrocarbon storage. So how is net to gross ratio calculated? The formula in the middle shows N over G is equal to HI divided by H. That is the net reservoir divided by the gross interval. So HI is sum of the sand layers, the total thickness of the sand productive layers. So H is the gross interval, the total thickness of the entire rock column, sand plus shale. Higher net to gross ratio, more productive reservoir rock. Lower net to gross ratio, more shale and less useful rock for hydrocarbon production. So why is net to gross ratio important? The top right formula OHIP calculation include the net to gross ratio because only the net reservoir rock matters when estimating oil and gas in place. The bottom right image shows a cross section of a real reservoir with layers of gas, oil, and water trapped in sand formations. So, the final takeaway is net to gross ratio helps petroleum engineers estimate how much of formation can actually hold hydrocarbons. It's important for calculating oil and gas reserves and deciding if drilling is worth it. A high net to gross ratio means more oil and gas potential, while a low net to gross ratio means more non-reservoir rock shale.